Alright, hello ladies and gentlemen, welcome back to this lecture series. Today we're discussing the third of the deformation methods, and this method will be called the principle of virtual work. This is an energy method, so anytime we're looking at the structural system, we're interested in energy that is going into the system and energy getting absorbed by the system. So in this example, or with this method, we're interested in how work done by external forces is in fact equal to the work that is absorbed by the structural system. And I'm going to refer to these as UE and UI. The general procedure that goes into the principle of virtual work is as follows. So we're interested in external forces and internal energy. So what we have is the sum of the external forces and external displacements combined is equal to the sum of the internal forces and the internal deformations. So that's a U and that's a delta. So to begin with, I'm going to list two equations. One's going to be for trusses, and it's going to be 1 delta is equal to sum of the virtual forces, real forces, lengths of the elements, the area of each element, and the elastic modulus. And I'll list the second equation, which equals 1 delta is equal to integral, which is also a sum of the virtual moments, real moments, elastic modulus, moment of inertia, dx. And I'll explain in a minute through an example how we use these equations to take advantage of the principle of virtual work and to solve for external deformations and displacements. So let's start with an example. In this example, we have a truss structure, and one thing I should probably do is write down example. And this truss structure has a brace, and it's only a single diagonal. Here it is. There is a roller support at one end, and a pin support at the other end. And what we have are A, B, C, and D. These are our joints, and we have point forces, 4 kilonewtons, and 5 kilonewtons applied here downwards. And the lengths of our members are 1.5 meters in height and 2.0 meters in length. And what's being asked of us is, what is the vertical displacement, or delta, at location C, dy at C. That's what we're interested in. So we're interested in how this joint at C moves downwards. The first thing that we're going to do is to solve for these forces that are shown, and that involves drawing a free body diagram and really solving for this truss structure. And if I did the math correctly, I should have the following compressions and tensions in each of the members. Okay. Now, the next thing we're going to do is introduce virtual forces. So what I'll do is I'll apply force going downwards. It will have a magnitude of 1. And the reason why I'm doing this is because the question is asking us, what is the vertical displacement at location C? Okay, so I need to draw a second truss structure and show its brace. There it is. And to really indicate what the forces are inside this structure as a result of the virtually applied external force. And we'll have as a force of 1 kilonewtons in compression in this member on the right. So having done that, we need to formulate a table now. And this table, what I need to do is to write all my members. So I have member AB, AC, AD, BC, CD. You always want to take one more look to make sure none of the members are left behind, because otherwise your calculations will be incorrect. And then we're going to list our virtual forces. These are all the virtual forces, and they'll have units of kilonewtons. So in this case we have 0, 0, 0, and there will be a -1. With this method, compression will be negative. There will also be real forces in this table with units of kilonewtons, and I will have -5 here, 4, 4, and -2. And lastly, I would like to list the lengths of my members, which gives me 1.5, 2.5, 2, 2, 1.5. And lastly, what I want to do is to multiply all these 3 columns, the virtual force, real force, and the length of the members. And it's quite simple. I'll get 0, 0, 0, and 3.0. And so if I go back up here and I look at my truss equation, this is what I'm interested in. What I can do is to say that the 1 kilonewton that I applied in my virtual structure multiplied by the external displacement that I'm interested in, delta Cy, is equal to the sum of the virtual forces and the real forces divided by my structural properties. And what I need to do is to really plug and play now. So I have a 3.0 here. I have my unit conversion. It's very important to be consistent when it comes to units, because otherwise you tend to get magnitudes that don't make sense. You'll have structures that will be deforming by a meter or so, and that never happens in real life. And this is a fraction, so we have 400. These are the properties. That's the area, 400 millimeters squared, and the elastic modulus, because these are steel sections, is 2e5, 2 times 10 to the power 5. And newtons divided by millimeters squared, that's just megapascals. Okay, so when we solve for delta Cy, we tend to get some value in millimeters. In this case, it should be 0.0375 millimeters. Okay, now we do another example. This time it will be a beam example. In this case, we're going to have a beam, and this beam will have a length of 20 feet. So we're switching to the imperial units now. There is going to be a roller support here on the left. There will be a pin support on the right. The lengths we have are 5 feet, 10 feet, and 5 feet. And there's a point load of 8 kips that is being applied at that location, and we have points A, B, and C. And the questions being asked of us is, what is the displacement at C? So C is either going to move down or it's going to move up, and we're interested in finding out what that magnitude is. So again, the first step in this method will involve the following. I'm going to apply a virtual force at the location of interest. In this case, it's C. And my virtually applied force will have a magnitude of 1 kips. Again, this is virtual, and this is real. And what I need to do is to make sure I've drawn out my boundary conditions correctly. So I have a roller and a pin here. There it is. And we're told that the elastic modulus is 29 times 10 to the power 3 KSI, kips per inches squared, and the moment of inertia, 53.8 inches to the power 4. And what I need to do is to find my bending moment diagrams. In the first example, in the real one, I'll have the following condition. I'll have forces that look like this. So this is BMD real, and there is a magnitude of 40 kip foot here. So notice the feet. 1 foot has 12 inches. So later when we do unit conversions, let's keep that in mind, because a lot of these properties are given to us in inches, and the length of the beam is in feet. So we need to keep that in mind. And the next thing I'll do is to obtain my BMD diagram for my virtual forces. So this time it's BMD, virtual, and I'll have my moments going down again and up, and they will look like that. There will be a magnitude of 5 kip feet at this location here. Okay, so now we have the BMDs for the real structure and the virtual structure, and the question is, what do we do next? So this next segment will be to go back and look at the principle of virtual work equation for beams. And for this example, we have to we've already applied this virtual force, and we're interested in delta Cy, and we know that we need to calculate this integration equation, and with this equation we have our virtual moments and real moments. And so anytime you're faced with an integration like this, you typically need to refer to some sort of integration table. In this example, we're gonna use this integration table that is available in this textbook that I'm using. It's called Hibbler. I got the 8th edition, and for this example we're seeing that at every segment of our beam, I'll divide it into 3 segments. So we got segment 1, it's right here, that's segment 1. We got segment 2 and segment 3. So again, we got segment 1, 2, and 3. What we notice is that segment 1 in the real structure corresponds to a moment of 0 in the virtual structure. So we can kind of ignore that because they kind of multiply and result in a 0 resultant. Segment 2 is interesting because the values are not 0, so we're going to kind of use that. And again, segment 3 in the virtual BMD corresponds to a 0 segment in the real BMD, so we can kind of ignore that. They're going to multiply, kind of, and cancel out to be 0. So we're only going to look at segment 2. And we can see we have triangles whose heights are in sort of inverse positions. One's on the left and one's on the right. So I'm going to go to my integration table. And what I have here is this triangle down here and this triangle up here, and I'm kind of noticing that the heights are in inverted positions, and I'm seeing this integration resultant, which is 1/6 m prime times length. So I'm gonna use that as the resultant when I solve this equation down here. Oops, there we go. So what I'll have is the 1/6. My first height here, the first height of the triangle will be 40. The second height will be a 5. And my length will be 10 feet. And so when I solve that, I will have 333.3 kips squared feet cube. And it's very important to keep the units consistent. Make sure nothing is left out, because if something's left out, you probably have made a huge mistake and your calculations won't be correct. Okay, and so what we have is the 333.3. I'm going to refer to it by 1,000 divided by 3. The virtual force we applied here was 1 kips. And we need to apply the properties EI. And when we do that and we do the unit conversions, we end up with the following. So let's do that. We have 1,000, 12 inches per feet. So that's cubed. We got the 3 here. 2093. 53.8. That's inches to the power 4. This was my moment of inertia. And lastly, I end up with a delta C of 0.369 inches in the downwards direction. And you can kind of see it's in the downwards direction because my point load, my externally applied point load, was in the downwards direction, and I ended up getting delta that's in the same direction, and everything worked out fine. One thing you need to keep in mind is that when you're solving for this equation here, you need to make sure that you enforce this 1 kips by bringing it to the right side of the equation and dividing it. Otherwise your units won't work out. So this 1 kip will cancel out with the square here, and you will just have a kip situation going on there. And that's it. We have solved the vertical deflection at location C. Let's call it delta CY. And if you're interested in the deflection at any other point along the beam, what you need to do is, again, to apply a virtual force, an externally applied virtual force, and do the same mathematics, follow the same steps, and you'll end up getting your deflection at that exact point. So the principle of virtual work is very interesting. It's not too difficult, but you need to do a lot of math for just a single result. So in the future, we'll discuss other methods that are more efficient with the same amount of math, you're going to be able to obtain more results, more deflections, and we'll cover those in the next lectures. All right, have a great day.